Hi there. Welcome to the practice set on multiplying polynomials. Please like this video if you find it helpful, subscribe for more math content, and drop a comment or a question below to engage. And as I've said in the last couple videos that I've recorded, and it's probably going to go on for a little bit, work being done in the apartment above me and important phone calls coming through on the phone. So if you hear some other noises, just roll with it. Normally, I would prefer it to be quieter, but pause the video to work these problems on your own and then come back to check your work. Okay, now, as I mentioned in the lesson for this, I am going to be multiplying these using a structure called the area model, which is based off of the base times the height is equal to the area of a rectangle. And so we take these more complicated problems and we break them up into like smaller little rectangles and we just add them all up at the end. So that is how I'm going to be doing it. If your teacher does not want you using the area model, okay, then one, don't use it. But you can check out the video that I have that compares and lays out different methods side by side. So you can figure out how does the work that I'm showing in this video, like what would that look like if you were to do it using distribution. Okay, so for this first one, I'm going to go ahead and put the 2x plus 1 as my base and my x minus 3 as my height. 2x times x is 2x squared. X times 1 is 1x. 2x times negative 3 would give me negative 6x, and negative 3 times 1 is negative 3. And then we see our like terms. Those are the things that we would be adding together. And so my final answer, the area of the entire rectangle, is 2x squared. And then negative 6x plus 1x is negative 5x. And then we have the minus 3. And you do need to make sure that you add them up. Every year I will have some students that will multiply everything. They'll put it into the smaller rectangles and then they just leave it. But remember, we're looking for the product, the base times the height of the entire polynomials. So what we want is the area of the entire rectangle. That's what we want, the area of the entire rectangle. So don't stop partway through. Okay, for this next one, let's change it up a little bit. We'll put the 3x plus 2 as the height and the 4x plus 1 as the base. So 3x times 4x is 12x squared. 3x times 1 is 3x. 4x times 2 is 8x, and 2 times 1 is 2. And once again, you're just going to notice where are those like terms. So we will have 12x squared, 8x plus 3x is 11x, and then we have a plus 2. And that is our answer. Third one. So I just tried to change these up with the signs a little bit. So you've got some, a plus, 2 pluses, 2 minuses, and one with a plus and a minus. There are some patterns you want to look for there. Just in terms of the signs. So x times x, so I did x plus 3 as my base and x minus 5 as my height. X times x is x squared. X times negative 3 is negative 3x. Negative 5 times x is negative 5x. And a negative times a negative will give me a positive, so that'll be positive 15. And we have our like terms. So our final answer would be x squared minus 8x. So negative 5x plus negative 3x is negative 8x plus 15. So just notice if you did the problems part way, just kind of be observant. If you're practicing and you're making some mistakes, it's totally okay to make mistakes, especially when you're brand new to doing these. But notice, like, where are you making mistakes? Did you leave off the negatives when you were setting up your area model? Did you leave them off when you were distributing or multiplying them a different way? Did you not add them together? Did you make mistakes when you added them together? What are those mistakes? Because if you recognize those mistakes, you can head them off in future problems. Now they get a little bit more challenging. So this one here, I think number 4, it's really just a matter of just the size of the numbers. I decided to to get a little bit bigger with the numbers. So we have a 6x plus 5, and we have an x minus 3. I guess that's not too big. X times 6x gives me 6x squared. X times 5 is 5x. 6x times negative 3 is negative 18x. And negative 3 times positive 5 is negative 15. Here are my like terms. So I have negative 18 plus 5. So that will be negative 13x minus 15. Now, the next ones get into like yuckier polynomials, and you could see, I mean, somebody could give you something awful with, you have this huge rectangle that you'd have to draw. But typically, no. Typically, the biggest problems that you'll see are 3x3s, which I think I have on the next slide. That's as big as it would get, and not that you couldn't see something bigger, but you usually don't. Now for this one, I typically will set up the rectangle so that the longer side is the base, but I'll do the next one differently just to change it up. So my height is the x plus 3, and then we have the base is x squared plus 2x plus 1. And then we just do all the little tiny problems. So x squared times x is x to the third. X times 2x is 2x squared. X times 1 is x. Second row, 3 times x squared is 3x squared. 3 times 2x is 6x, and 3 times 1 is 3. And a huge advantage to using the area model is the placement of your like terms. Maybe not on the diagonals, but close to. So we've got x to the third, which does not have anything to combine with. 3x squared plus 2x squared is 5x squared, and 6x plus x gives us 7x, and then we have the plus 3. And there's our final answer. And for this last one, just to show you that you can set it up other ways, I don't usually do it this way, but you can. So this time we'll put the 2x minus 3, we'll just make that the base, and then we'll have the longer polynomial going down the side as the height. So x squared minus 4x minus 1. X squared times 2x is 2x to the third. X squared times negative 3 is negative 3x squared. Negative 4x times 2x is negative 8x squared. Negative 4x times negative 3, that'll be a positive 12x. 2x times negative 1 is negative 2x, and negative 1 times negative 3 is positive 3. And you should see that we still have our like terms sitting on the diagonals. So that does not matter. It's basically you're just turning the rectangle another way. But if you picture like an index card or something that's rectangular and you wanted to find the area of it, it wouldn't matter whether you were holding it like side to side or up and down. I guess in elementary school sometimes it's called the hamburger and the hot dog bun. Like if it's a piece of paper, it has the same amount. It's the same amount of paper. Regardless of how you're holding it. So you can set it up either way. 2x to the third, what do we have here? Negative 8x squared plus negative 3x squared is negative 11x squared. This one I would probably think of as 12x minus 2x, which is 10x, but you can think of it as adding as well. And then plus 3. Okay, so there are the first 6 and potential layouts of the work using the area model. I'm just showing you some versatility. Now, this is probably the worst kind of multiplication problem that somebody would give you. If your teacher is giving you like a cubic times a cubic, so it's like a 4 times a 4, I'm sorry if your teacher's doing that to you. But the area model is probably your best bet for doing that because it's going to have a lot of pieces to it. All right, so we've got x squared plus 2x plus 1, and then for our height, we have x squared minus 3x plus 4, and we just have all these like we have nine little multiplication problems that we have to do there. A great advantage to the area model too is when you set it up, you have a box open for every single one of your little multiplications. And if you do this using distribution, you don't have the little boxes. So if you miss one of them, you just kind of miss like doing one of the multiplications, because you got 9 multiplication problems to do there, and you missed one, and you might not even know that you missed it. But with this model, you will know if you missed it because there'll be an empty box. So x squared times x squared is x to the 4th. X squared times 2x is 2x to the 3rd. Now, if you're just kind of blanking out on that, like x squared times x squared is x times x times x, and you can see, oh, look, that is x to the 4th. So if you need a refresher on that, please go check out the video on laws of exponents, like what do we do with our exponents. That's a loud sound. I don't know if the computer picked that up. Some very loud hammering. Anyway, x squared times 1 is x squared. Next line down, x squared times negative 3x is negative 3x to the 3rd. Negative 3x times 2x is negative 6x squared. And then multiplying by 1 is nice because it'll just be itself, so negative 3x. And then last one, 4 times x squared is 4x squared. 4 times 2x is 8x, and 4 times 1 is 4. And our awesome method here puts those like terms right where we can find them easily. And even if they're not on the diagonals, okay? And I probably should have put one in here where they didn't wind up on the diagonals, but I didn't. But even if there was one, they'd be close by. You don't have to look all over the rectangle for them. So x to the 4th doesn't have any friends. We have negative 3x to the 3rd plus 2x to the 3rd, so that's negative 1x to the 3rd, and of course you do not need to write the 1. Now we've got 3 things going on here. So we have 4 minus 6, so that's negative 2. So 4x squared plus negative 2x squared, negative 6x squared is negative 2x squared, and then negative 2 plus 1, remember that is a 1, would give me negative 1. So this will be negative 1x squared. 8x minus 3x is 5x, and then we have the plus 4. And if you don't want to write the 1s there, you don't have to. It's not wrong to write them, but you just do not need to. Okay? So that's how that looks. And if you did this the other way, and if you want to, please watch that video where I do a 3x3 and I do it with the area model, and then I do it with distribution side by side, and it becomes very clear that there are some obvious advantages to doing this way. So there we go. Now for these last 3, it just says, what do you notice about them? So these are what we call a special case. So notice something about each of these problems. So you have 2x and a 1 and 2x and a 1, but one of them has a plus and one of them has a minus. X and a 4, but one of them's plus and one of them's minus. And then just to make sure we don't get too stuck in a rut, 3x minus 2, 3x plus 2. And again, same terms there, the 3x's and the 2's, but one of them has a minus, one has a plus. So you've got these opposite signs, but everything else about those factors are the same. And so we want to kind of pay attention to that. What might these do? So let's look at this first one. So we have 2x plus 1 and 2x minus 1. And of course, the order doesn't matter. It doesn't matter whether the plus is in the first parenthesis or in the second parenthesis, because you can put them on either dimension of your rectangle, like, because 2 times 4 is the same as 4 times 2. Multiplication is commutative. So we have 2x times 2x. Well, 2 times 2 is 4, and x times x is x squared. Here we have a positive 2x. 2x times negative 1 will give me a negative 2x, and then negative 1 times 1 is negative 1. And when we go to look at our diagonal, what I see are opposites. So I have the 4x squared, but then negative 2x plus 2x is 0x, and then 0 times x is just 0. So there is no reason to write the 0x. So that middle term drops out. That is a missing b term. Okay, we've talked about that in earlier videos when we were solving quadratics. We can solve using square roots if we're missing the b term. So it actually dropped out. Let's take a look at the next one. So we have x plus 4 and x minus 4. So x times x is x squared. x times 4 is 4x, x times negative 4 is negative 4x, and negative 4 times positive 4 is negative 16. And we see this happening again. We have negative 4x plus 4x, which is going to cancel out, and all I'll be left with is the x squared minus 16. And last one. Okay, so we'll do 3x minus 2, and we have 3x plus 2. 3 times 3 is 9, x times x is x squared. 3x minus 2, or times negative 2 is, negative 6x. 3x times positive 2 is positive 6x, and 2 times negative 2 is negative 4. And we see this for the third time in a row. We see something once, we're not sure. Twice, we think, maybe. And by the time you've seen it for the third time, we think this looks like it's probably a pretty reliable pattern. And it is a pretty reliable pattern. So we have 9x squared. These two cancel out because 6x minus 6x is 0, and we're left with a minus 4. And what we want to notice is the pattern of the answers. So a couple of things to notice about them. First, the middle term dropped out. So in all of these cases, the B piece of it dropped out. And then if you look at what's still there, we see a pattern in the numbers. So we see the number 4, the number 1, the number 16, the number 9, the number 4, and those numbers are what we call our perfect squares. So if you think about, okay, the perfect squares, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and there are more, okay, so we could have like a 25, but the numbers that are left happen to be perfect squares, okay? So just kind of file that away. We want to always be observant and looking for these patterns. Because this is what we call a special case. And when we reverse the order, you'll notice that we'll be on the lookout for problems that look like this, that fit that pattern. All right, so don't forget to like and subscribe if you found this video helpful. Ask a question or drop a comment below, and check out some of the other videos on the channel, including some of the other videos that are related to multiplying polynomials, including the video on algebra tiles, using algebra tiles to do it, and our comparison contrast of the different methods. So please check those out if you think they would be helpful, and I will see you in the next video.